Sir, can you hear me?
Sir, your microphone is off. Sir,
So your mic is muted, sir.
Oh, okay. Thank you. So now, can you hear me?
Yes, sir.
Okay, good. So Gaurav, you wanted to say something?
Yes, sir. Sir, I wanted to ask that since we have our chemistry class test tomorrow, uh, can you kindly take the test on Friday instead of tomorrow?
That is a problem because it's a huge class. If I say that the class test will be uh, on uh, on Friday, and if some of you have a problem, they can object that. So then you have to be sure that no one has a problem if I take a class test on Friday.
So actually, yesterday our CR took one poll, and in that, maximum number of students agreed that they wouldn't have a problem on Friday.
No, it's not about the maximum. In this case, I will not go for the maximum. I will go if all of you do not have the problem. Because it's about a test and which carries marks, right? So if few of you have a problem, then that's not fair. And but this test was announced at least 1 week ago, right? I mean, uh, then is it not possible for you to change the test for the chemistry?
Chemistry was announced earlier, I think. I don't know why.
Then why did you people not tell me earlier? I could have then discussed within. I could have asked if somebody has a problem. But when is the test tomorrow for chemistry?
Afternoon time.
Oh, then you have
After
enough
12.
time. Then it's fine. Then you have enough time, right? I mean, because the test, the class timing for maths is 10 to 11 tomorrow, and your
Yes, sir,
chemistry
but
is 6.
studying for both, that would be a little hectic.
But you people knew that. I tell you that the problem is to change in the last moment, because if you would have told me earlier, I could have discussed with you people. Now, if I change the date, and if somebody object that I had a problem, that's why I could not took the test. Please rearrange the test for me. Then again, I have to rearrange it.
Okay, okay,
So
sir.
that is the problem. So if you have a problem, please tell me little bit in advance so that I can write you in email, give you a time. Okay, within 2 days, please reply if you have any problem. And if somebody has a problem, then again we have to figure out some time which will be convenient for all of you.
Sir, actually, in that poll, 104 students had taken, and 99 told that it would be better on Friday. But 5 students did not think that Thursday, tomorrow.
Yeah, that's the problem. And if forget about the 5, if one student said that I have some problem on Friday, so I can't take the test,
Yes,
then
yes.
I will be the problem. Okay, since
Okay, sir.
means if you people have a problem on tomorrow at 10 o'clock, I can say that no, I will not listen to anybody because it's a normal class hours, so I can take the test. So if some of you have your own personal problem, I will not care, because you are supposed to attend the class hours, right? But except from the class hours, if I go beyond the class hours, then I have to take concern from all of you. especially if I conduct a test which carry marks.
Yes, sir, I get you. Yes.
Okay, so that is the problem now to change it. If you could have told me earlier, I would have, I mean, write an email and try to fix a time. Yeah, Shaunak, you want to say something?
Yes, sir. Gaurav is telling about Friday because in that Friday from 3 to 6, we used to have one physics class, physics lab. But in this Friday, they will not conduct the class, so you can take test because no one will have class during that time.
Right. But if somebody said that since I knew that there will be no physics class on that day, so I had some pre-planned, something in my schedule.
But if anyone says that I have pre-planned, they will get another extra day for studying maths.
Another extra day for studying maths does not matter. They get another day for extra day for studying maths. It matters if they could not take the test, and that will be a problem.
Okay.
Right? You got the point.
Yeah, yeah.
So that's the main point. If I conduct the test out of the class hours, then I have to take consent from all of you. It's not I have to go with the majority. Even it within a class hours of some other subject, because people may say that yeah, I knew that the physics class will not be take place, and I have some other assignment or some other occupancy, and then that would be a problem. Hmm. So can you okay, I mean, it's needless to say at this moment to now talk to your chemistry. Yeah, so if possible, then you can then contact your chemistry teacher and say that during the lab hours, probably your chemistry, you can take the test or something like that. I don't know. But for me now, it's little difficult to change the timing of the test. I can I can say that, okay, let's try to fix it will be on weekend. But if somebody said that no, I'm not free on Friday, I'm not free on Saturday, I'm not free on Sunday, then the next week onwards we will have the exam week. Then for me it will be difficult to figure out a time for conducting the test. Okay, so if you come up with 100% no objection poll, then I will accept it. But if one of you objects that you have a problem, then I have to retake the test for that person separately, and that is the problem. Okay, is it fine? Do you get my point?
Yes, sir. Okay, sir.
Okay, so sorry, I mean, this time I can't help you in this way.
So the portion is only the linear algebra, right? Or
Right.
okay, sir.
Only on linear algebra. Yes. Okay, let's start.
Sir, actually, this week so many tests are going on. We just lost track which test is coinciding with which.
Right, I know that. I mean,
We
the
also
last
have
moment.
multiple tests.
Last moment it happens that there will be multiple tests and so on. It happens sometimes in the last moment, so that's why it's better to that you keep your track, and then according to that you request the instructor. If you people would have told me earlier, I would have conducted the test today, for example.
Sir, today also we have two exams.
We finished one in the morning and
We
we have
finished
one in the
one in the morning.
afternoon.
Yes, sir. One
Okay,
in the
okay.
afternoon.
I'm sorry, but this situation happens. I mean, in the last moment, people take test. But yeah, if you could talk to your instructor and previously try to schedule so that the two tests does not occur in the same day. But you also lost track. That's the problem. Okay. Anyway, so I told you the problem from my side. So if you come up with what I said, that if you come up with a no objection from all of you, then I do not have a problem to take the test. But I don't want to take two class tests. Two class tests in the sense means if somebody could not attend, then that person will have a chance to say that please take a retest. That I don't want to do that. because especially making the questions for multiple choice in the WeLearn, it takes really time. Okay.
Yes, sir. Okay, sir.
Okay, let's start. Sorry. So today we'll discuss kernel and image of a linear transformation. Okay, so first I write down the definition. Let's say that you have a linear map from V to W. Let's be a linear map. Then the kernel of T, then the kernel of, oh, okay, sorry, kernel of T. Actually, this is usually denoted by KERT and is defined by you take all the vectors belongs to V such that these vectors will be mapped to the null vector of W. Okay, so you take this set of vectors and this set of vectors is called the kernel of T. Clear? So the kernel of T is the set of vectors in V. That means kernel of T is a subset of V, is a set of vectors in V such that this set of vectors will be mapped to the null vector in W by this linear transformation T. Since it's related to T, that's why it's called the kernel of T. Okay. And image of T, this is easily denoted by image of IMT and is defined by IM. Okay, let's write down. It's defined by image of T is the image of actually V with respect to the linear map T. So that means there is the set of vectors in W such that TV equals to W for some V belongs to capital V. Okay, is it clear? So that means the image of T, it consists of the vectors from W. whereas the kernel of T consists of the vectors from V. Okay, so that means image of T will be a subset of W. Now we have a note. What's about the null vector of V? Will it belong to kernel of T?
Yes.
And why?
So because when you do linear transformation on a null vector, it
Mhm.
will result in the null vector itself.
Right,
Yes,
right.
sir.
The other domain, because these two null vectors are maybe different. If you have a linear map from, let's say, R2 to R3, a null vector in R2 is different than the null vector in R3. So that's why the null vector will be always mapped to the null vectors of the other domain. So that's why the null vector in V will belongs to the kernel of T. Okay, let's see the other things. That null vector of W, does it belong to the image of W?
Yes, sir.
Image of
These
what? Image of W.
sorry,
Image
image
of
of T.
null of
Sorry, image of T. Image of T. Image of T. Yes, and what is the reason?
Theta V corresponds to theta W.
yes, sir. The exact opposite of the
Yeah,
first one.
yeah, right. Okay. Now, if you take kernel of T, which is a uh, subset of V, and the null vector of V belongs to kernel of T, then the natural question comes into our mind that does the kernel of T form a subspace of V or not? And yes, if you take any two vectors from kernel of T, it is easy to show that their linear combination will also belong to kernel of T. Right? You can easily show that. And similarly, the image of T, if you take any two vectors from image of T, it is also easy to show that since T is linear, then it's easy to show that their linear combination will also belong to the image of T. So what I said that uh, if you take, let's say, okay, write down like this, alpha I Vi, this summation will belongs to kernel of T when Vi's all belong to kernel of T and alpha i's belongs to some real number. This is also true that if you take, let's say, beta I, Wi belongs to image of T when Wi belongs to image of T and beta i's are some real numbers, right? And that's why we have a we can say that what I say uh, just right now, they form the subspaces. So kernel of T is a subspace of V and image of T image of T is a subspace of W. Okay, it's easy to prove. It is also given in the assignment to prove it. Another note, there is a term called nullity. Nullity of T. Since the kernel of T form a subspace, and the dimension of that subspace we call nullity of T, or nullity of just nullity T. Okay, clear? So dimension of kernel of T will be called the nullity of T. Similarly, there is also a name for dimension of image of T, that is called the rank of T. The rank of T is the dimension of the subspace image of T. Okay. Now let's explore with an example. Let's say we have a linear map from R3 to R3, and it is given, the map is defined such as, if it takes a vector x, y, z, then it will map to, it will map to a vector whose first component is x plus z, second component is x plus y plus 2z, and third component is 2x plus y plus 3z. Okay, and we have to find the kernel of T and image of T. Okay, so what we know, that kernel of T then will be will be the set of vectors x, y, z such that T, x, y, z equals to 0, 0, 0, this null vector, right? So that means x equals to 0, y equals to 0, and z equals to, so that means T, x, y, z. So the transformation is given by this formula. That means x plus z equals to 0, x plus y plus 2z equals to 0, and 2x plus y plus 3z equals to 0. Right? Okay. Now, if you solve this equation, you easily figure it out, that we can say that z equals to minus x and y equals to x. Okay. So that means the second term and third term can be represented by the first term. So that's why now the kernel of T can be written as x comma minus x. To RQ, this is nothing but the set, let's say x into 1 comma 1 comma minus 1, where I can say that x belongs to the real number. And what is this subspace then? So
Straight line.
this subspace consists of the vector 1 comma 1 comma minus 1 and its and its multiplication with a real number. So that means there is a straight line from 0 to this coordinate 1 comma 1 comma minus 1. So of course, just a note in this case, but we can see that dimension of kernel of T so just first I write down that this kernel of T is form a straight line, right? Straight line, and that's why the dimension of kernel of T equals to 1. Now we have to find the image of T. So let's take a vector x, y, z. In R3. Of course, here R3 means this is if we map from T is mapped from V to W, then this will be actually W. Now, if x, y, z, this vector belong to the image of T, then there must exist an vector, let's say x1, y1, z1 in RQ means R3. In this case, R3 is V. Okay. So that means T of, and okay, there exists this vector such that if we take the linear transformation of this vector x1, y1, and z1, it will become x, y, z. This is by definition. Okay. So from here, we know that the formula for the linear transformation is given here. Now we apply for the vector x1, y1, z1, and we get x1 plus z1. Now we equate component wise equals to x, x1 plus y1 plus 2z1 equals to y, and 2x1 plus y1 plus 3z1 equals to z. Here also you can, from here you can easily figure it out that if you can eliminate x1, y1, z1 and figure out the relation between x, y, z, which is x plus y equals to z. So that means the third component of the in vector x, y, z can be represented by the addition of the first two components. So that's why we can just write down
Now it will be
this.
a plane.
Right. X, y, if x, y, z belongs to image of T, then x plus y must be equals to z. So that means image of T consists of the vectors x, y, z. Sorry. So instead of writing consists of the vector x, y, z, we can write down consists of the vectors x comma y comma x plus y, right? And this is nothing but we can write down in this way. Okay, let's write down this is RQ, and this is equals to, now I write down this vector x comma y comma x plus y as a linear combination of two vectors in this way. First, I take the x, which is the real number, and we can see that in the first component and third component there is x. So that's why we put the 1 for the first component, 0 for the second component, and 1 for the third component. Plus, similarly for y, we can see that y does not exist in the first component, so we put 0. Y exists in the second component, that's why we put 1. And y exists in the third component, that's why we put 1. Such that x and y belongs to R. Right? So here we can see that x, y could be, I mean, they are real numbers, and this set of vectors is represented by the linear combinations of these two vectors, 1, 0, 1 and 0, 1, 1. And these two vectors are linearly independent, right? They are not linearly dependent. They are linearly independent. That means the subspace image of T, it is spanned by these two linearly independent vectors, 1, 0, 1 and 0, 1, 1. Of course, we know that if two vectors, I mean, they're linearly independent and they span a space, that will be a plane. And the dimension in this case will be 2, right? So here we know that this is a plane. And then dimension of image of T will be 2. So here also we have an observation that here we get the dimension of kernel of T equals to 1, and dimension of kernel of T, and dimension plus, if we take the dimension of image of T, which is 1 plus 2 equals to 3. And that was actually the dimension of 3. Okay, so these are our observation. So this R3, actually we can say that if this R3 is the left hand side, we can say left hand side R3. That means if T maps from V to W, this dimension of kernel of T plus dimension of image of T will be actually the dimension of V. And with this concept, I mean, you can prove this one, and a important theorem came up with this property, which is called the rank nullity theorem. Okay, so rank nullity theorem is with this concept. It's very important theorem. It's useful in many cases. It's called rank nullity theorem. What is rank nullity theorem? Let's say that T is a linear map from V to W. Of course, I mean, we are not saying that V is a finite dimension and so on, because in our case, we are restricted with up to R3. Then dimension of V, you can say this is equals to dimension of image of T plus dimension of kernel of T. So that means this dimension of image of T, as we call it, rank of T. And as you know, that dimension of kernel of T is called the nullity of T. And that's why it will be called the rank nullity theorem. So if you have a linear transformation T from which maps from V to W, the rank of T plus nullity of T will be always equals to the dimension of V.
Actually, this sort of theorem we had seen in mathematical methods course in the matrices part.
Yeah. So here also it's given to prove this one as an assignment. So you can prove this one. It's not difficult. So there are cases and proofs are given in every books. Yes, you may go through the proofs. Okay. So I just take another example. Just to get there, let's say that again we have a map from R3 to R3, and the map is given like x plus y plus z, comma 2x plus y, sorry, plus 2z x plus 2y plus z. And here x, y, z belongs to the real number set. And we have to find or verify the rank nullity theorem.
So could you please scroll up?
This one or more?
Yes, sir. Means I want to see the question, sir.
Oh, okay. Sorry.
Yes, sir. Okay, sir.
Verify rank nullity theorem. Yeah. So again, as we know that the kernel of T will be the set x, y, z, these vectors, such that the T of these vectors will be the null vector. And now from the formula of the given transformation, we can write down x plus y plus z equals to 0, 2x plus y plus 2z equals to 0, and x plus 2y plus z equals to 0. Okay, there are many ways to solve this one because these are the homogeneous equation. So I take first two, and from here we can write down that. I hope that you already know the techniques from the math methods. One, solving the homogeneous equation. Let's say this is a constant. So this can give us x equals to k, y equals to 0, and z equals to k. And now we verify this solution in that last equation, means here. And it verifies. That's why the last equation is also satisfied with the solution. So that means we get the relation between the components, that if we take x equals to k, then y term, the middle component will be always 0, and the last component will be the negative of the first component. So that's why we can write down that in this case x, y, z equals to some k, some real number k, into the vector 1 comma 0 comma minus 1, such that k belongs to the real number. Of course, here also you can see that this is a straight line. So that's why the kernel of T is 1 comma 0 comma minus 1 belongs to R, and that's why the dimension of kernel of T will be 1. Okay. Now we have to find the dimension of image of T. We proceed a little different way. Let's say that B1, B2, B3 is a basis of the domain space R3. Okay. So of course, as I told you that when we have a linear transformation which maps from, let's say, V to V, and so a vector means to know that after the transformation, where does a vector go, we just can derive it if we know that where does the basis go, right? So that's why if we take B1, B2, B3 is a basis of the domain space R3, then the image of T is a linear span of vectors TB1, TB2, and TB3, right? So if a vector in, so since B1, B2, B3 are the basis, that means any vector in V can be represented by the linear combination of B1, B2, B3. In the same way, the TV after the making the transformation of V, the TV also can be represented by the linear combination of TB1, TB2, TB3. But remember that this TB1, TB2, TB3 may not be linearly independent, but their linear combination will, can make the vector TV. Okay. Now, so this is a piece of information we know. Now, in this case, we take, instead of B1, B2, B3, we take our standard basis E1, E2, and E3 as, sorry, basis of hierarchy. Then we have to find TE1, and we find from the formula for the linear transformation E1, as you know, that 1 comma 0 comma 0, and if we put that one, we'll figure it out. This is 1 comma 2 comma 1. TE2, we'll figure it out. This is 1 comma 1 comma 2, and TE3, this is equals to 1 comma 2 comma 1. Of course, as I told you that when the basis will be transformed, they may not be linearly independent anymore. It may happen, but their linear combination can form any vector, any transformed vector with the same linear transformation. So here our observation is that these two vectors are the same, and these vectors and these vectors are linearly independent. So that means image of T is a, we can say that this is a linear span of the vectors 1 comma 2 comma 1 and 1 comma 1 comma 2, and which are linearly independent, right? And that's why the dimension of image of T will be 2. Of course, in this case, we find the rank of, this is rank of T is 2, and nullity of T is 1. 2 plus 1 equals to 3. Yeah, Pritish, what is your question?
Yes, sir. Here E1, E2, E3 is the basis for vector space V.
So if you think in terms of T maps from V to W, then this is the basis for the vectors space V.
Okay.
Okay. So
Here it is only for R3 to R3.
here it is, the example is from R3 to R3.
Okay.
Okay. So for the simplicity, you can think that if a linear transformation maps from, let's say, V to V, and if, let's say, B1, B2, B3 are the basis for V, then, and if you ask that if you take any vector, let's say small v, where does it go? And as we discussed that if we have the linear transformation of this b1, b2, b3, that means tb1, tb2, tb3, with their linear combination, you can represent transformed vector small v.
Yes, sir. Now it is clear.
Okay, where v is any vector in capital V. Okay, is it clear?
Yes, sir.
So,
Fine.
so here also we get the rank of T plus nullity of T equals to 2 plus 1 equals to 3. This is equals to dimension of V, or in this case R3. Okay. Now, one important property that I write down in terms of theorem. So as we know that if you have a linear transformation, let's say the linear transformation is from V, for the simplicity, let's say it's from V to V. Now you take a basis with respect to that basis from both of the domain, the left side V and the right side V. We can represent T with respect to a matrix with a different, with relative to the different basis. You represent the T in terms of a matrix, right? So it does not, but it does not matter. So as I told you that since after the transformation, this will be represented, the any vector will be represented by linear combinations of the transformed vector of the basis, right? And that's why if you take one basis, whatever the transformation you get, that means whatever the rank you get, for that transformation. So this will be same if you take the another basis. Okay, and because this rank depends on the T. And now the rank of the matrix for the first case will be the same as the rank of the matrix for the second case. Actually, what happens that rank of the matrix will depend, the rank of the transformation matrix will depend on the rank of this linear map T, and this will be equals. So I just write down the property. Property is, let's say T is a map from V to V, be a linear transformation then rank of T will be equals to rank of MT. What is MT? Where MT is the matrix of T relative to any ordered basis of V. Okay, so that means uh, if you have taken a ordered basis, some ordered basis, let's say standard ordered basis, if you get out the matrix for the linear transformation, the rank of matrix will be equals to the rank of this linear transformation. Of course, if you take the another basis, you find the matrix, since the rank of T will be equals to rank of that matrix, that means the rank of all these matrix with respect to different ordered basis will be the same. Okay, so you're running out of time, so you stop here. So do you have any question, comment, doubts? Please let me know.
So no matter what order we take, the number of independent vectors in the basis will be same. So the rank will not depend on the
Rank.
order, right?
Right. Because if you change the order, that means you have a different ordered basis. Though you take the same set of vectors, but if you change the order, means ABC is not equals to BCA in that way. If you change the order, of course your matrix will be changed, but the rank will be the same.
Yes, sir. Because the dimension will remain the same of that basis.
Right, and the nullity will be the same, right?
Yes, sir. From that theorem also we can say that since the dimension of the basis is remaining same, then the nullity also has to remain same because both their sum should be the original dimension of V.
But only you have to prove that the rank of T equals to rank of the matrix.
Yes, sir. Rank of that one basis.
Any matrix. Right. Matrix
So
related to
what do you
any
say
order
about
basis. Yes, sorry, Pritesh.
what do you say about the change the order? Change the order of
Oh,
which
okay.
first?
So Gaurav said that let's say that you take the ordered basis E1, E2, E3 and construct a matrix for that linear transformation. Then
Okay,
you
sir.
take the ordered basis E2, E1, E3. Your matrix will be
Yeah, yes,
different
sir.
since the order has been changed. So though it's a same set of vectors for forming the basis, but if you take a different order, the matrix will be changed. But of course, the rank for those matrices will be the same. Okay, any other question? Okay, so if not, then I stop here. So then all the best and good luck for your class test tomorrow. It will be only on the linear algebra portion. But for the mid sem, sorry, you have the end sem. For the end sem, the whole syllabus will be in the exam. Okay, so you have to cover all the syllabus from beginning to the end, whatever we have taught or learned. Okay, is
Sir,
there any
for
question? Yes,
Yes,
Gaurav.
sir. So for the linear algebra portion, it will consist of the parts that you have discussed in class, or the other parts are in the math methods also.
No, whatever I have discussed in the class, but of course, I have already taken granted that since you learn something, because we have used some methods that I have not explained, that because I assume that you have already know these methods from the math methods. Okay, so that will be assumed that you already know from the math methods. But of
Yes,
course,
sir.
the questions will be based on whatever I have taught. But
Okay,
for
sir.
some competition purpose, for some concept purpose, if it has been taught in math methods, that can be
Okay.
used. Okay, any other question? Okay, so if not, then I thank you all, and we have all the best and good luck once again for your exam.
Thank you.